Look, I've seen a lot of jobs out there. Some are clean, some are not. But when you're dealing with welding, there's no room for good enough. A good weld is the only thing holding a skyscraper together, keeping a bridge from collapsing, or making sure a pipeline doesn't burst. It's serious business. A bad weld is a ticking clock, a disaster waiting to happen. It's a weak link in a strong chain, and that weak link will always fail when you need it most. So, paying attention to weld quality isn't just about making things look pretty. It's about safety, reliability, and doing a job you can stand behind. It's about making sure the thing you built stays built. So what makes a weld bad? The experts at the American Welding Society, or AWS, have a simple way of looking at it. They call them discontinuities. That's a fancy word for any interruption in the uniform structure of your weld. Think of it like a bump in a smooth road. Now, not every bump is a problem. Some are small enough that you can drive right over them, but some are big enough to break an axle. A defect is a discontinuity that's too big or too dangerous to be acceptable. It's a bump that fails the inspection. It means the weld isn't strong enough to do its job safely. Our goal is to avoid those axle breakers. Let's take a real-world example. Imagine a welder working on a high-pressure pipe for a chemical plant. He's in a hurry, the light is bad, and he doesn't clean the metal properly before he starts. He lays down a bead that looks okay from the outside, but underneath, it's full of tiny gas bubbles, a defect called porosity. For a while, everything seems fine, but the constant pressure inside that pipe pushes against the weakened weld. One day, that pressure finds the weak spots and the weld cracks. The result is a dangerous leak, a plant shutdown, and a very expensive, very messy problem. All because of a few shortcuts. Understanding these defects is the first step to preventing them. It's not about memorizing a textbook. It's about knowing what to look for on the job, in the real world. It's about understanding what causes these problems and how to stop them before they start. This isn't just about passing a test. It's about being a true professional who takes pride in their work. Let's start with the worst of the worst cracks. A crack is exactly what it sounds like. A fracture in the weld or the base metal next to it. Inspectors have zero tolerance for cracks. According to AWS rules, any crack fails the weld. Period. They can be tiny, almost invisible, or big enough to see from across the room. Cracks can form when the weld is hot as it cools, or even days later. A crack means the metal was stressed beyond its limit, a direct path to catastrophic failure. Never leave a crack in a finished weld. Causes: mostly stress and brittleness. Wrong filler metal. Incompatible filler and base metal leads to weak bonds. Cooling too fast. Hot metal shrinks and builds internal stress. Thick or high-carbon steels are especially vulnerable. Contamination is another enemy. Oil on the metal, paint on the metal, moisture on the metal, hydrogen embrittlement risk. Detecting cracks can be tricky, especially small ones. Surface check. Visual inspection with good light. Use a magnifying glass to help. Next step, dye penetrant test. Spray colored dye on the weld. Wipe the surface clean. Apply developer. Dye reveals surface cracks. For subsurface cracks, use advanced methods. Magnetic particle testing on steel. Magnetic field shows surface, subsurface breaks. Ultrasonic testing for deep internal flaws. Radiographic, X-ray. Testing for internal defects. Fixing a crack. Remove it completely. No welding over or patching it up. Grind out the cracked area. Gouge out the cracked area. Machine out the cracked area until you reach clean, solid metal. Diagnose why it cracked before re-welding. Typical fixes. Preheat to slow cooling. Use correct low-hydrogen filler rod. Keep the work area bone dry and spotless. Prevention is better than cure. Grinders and rework are expensive. Next up are two defects that sound similar but are critically different. Incomplete fusion. Incomplete penetration. Incomplete fusion is when the weld metal doesn't fully melt and join with the base metal or join with a previous weld bead. Think of it like using a glue gun, but the glue isn't hot enough. It just sits on the surface instead of bonding. It creates a hidden weak spot right at the edge of the weld. The weld might look fine from the top, but underneath, there's a gap where the two pieces of metal never truly became one. This is a dangerous defect because it's often invisible on the surface. The causes for incomplete fusion almost always point back to heat and technique. The most common cause is simply not using enough heat. If your amperage is too low or your travel speed is too fast, the arc doesn't have enough time or energy to melt the walls of the weld joint. The angle of your torch or electrode is also critical. If you're pointing it too much at one side of the joint, the other side won't get enough heat and won't fuse properly. Another sneaky cause is letting the molten weld pool run ahead of the arc. When this happens, the liquid metal flows onto cold base metal and it won't fuse. It just sits there, creating a hidden trap. Incomplete penetration is a cousin to incomplete fusion. This happens when the weld metal doesn't reach the bottom or the root of the weld joint. On a butt joint, this means you can see a gap on the backside where the weld didn't burn all the way through. This leaves a built-in stress point right at the root of the weld, which is the perfect place for a crack to start, especially under vibration or load. Like incomplete fusion, it's a sign that the weld is not as strong as it needs to be. AWS standards have very strict limits on how much, if any, incomplete penetration is allowed, especially in critical applications. The fix for both of these problems involves controlling your heat and preparing your joint. For starters, make sure your amperage and voltage settings are correct for the material thickness you're welding. You need enough power to melt through the metal. Proper joint preparation is also non-negotiable. If the gap at the root of the joint is too narrow or the sides of the joint are too steep, the arc simply can't reach the bottom. You need to grind your joint to the correct angle and leave a proper root opening. Slowing down your travel speed also gives the heat more time to penetrate and fuse the metal completely. If you find either of these defects, the only fix is to grind it out and do it again, this time with the right settings and preparation. Let's talk about the edges of your weld. Undercut is a groove or notch melted into the base metal right alongside the toe of the weld. It happens when the arc's heat is too high or your technique is off, and you dig away at the parent metal without filling it. This creates a thin, weak spot. Think of it like digging a little ditch next to your foundation. That ditch is a stress point where cracks form, especially under load or flexing. A little undercut might pass some AWS codes, but too much will get the weld rejected every time. The causes of undercut are usually tied to three things: too much heat, wrong technique, moving too fast. If your amperage is cranked too high, the arc becomes a cutting torch, blasting the base metal. Using a long arc length spreads out the heat and can gouge the joint sides. Your electrode angle plays a huge part. Point the electrode at the sidewalls instead of into the joint, and you'll melt the edge without depositing metal. If you travel too quickly, the weld pool won't fill the area you melted, leaving that groove. Now for the junk that gets trapped inside: slag inclusions. This defect shows up in flux processes like shielded metal arc welding, stick welding, flux cord arc welding. Slag is the cooled flux layer that floats to the top of the molten weld pool. Its job is to shield the hot metal from the air, but bits of slag can get trapped inside the weld instead of floating out. That creates a void, a weak spot with no strength. It's like baking a cake with a chunk of plastic in it. Preventing slag inclusions is about cleanliness and technique. On multi-pass welds, you must clean all the slag off the first bead before the next pass. Use a chipping hammer and a wire brush. If you weld over slag, you'll trap it. Your travel angle matters. Too steep and the arc pushes slag ahead of the pool, where it gets trapped as metal solidifies. In tight corners or deep grooves, slag has a hard time floating out, so be extra careful and give the slag a path to escape. Sometimes, the problems are right there on the surface for everyone to see. Let's start with spatter. Spatter is those little balls of molten metal that fly out from the welding arc. They stick to the base metal around the weld. While a small amount is unavoidable, excessive spatter means something is wrong with your setup. It's not just ugly, it's a waste of filler metal. It also creates a mess that must be cleaned up, costing time and money. Those hot balls can damage sensitive surfaces. They can create small, hard spots on the base metal. Those spots can start corrosion, or they can start cracks. What causes all that flying metal? Usually issues with machine settings, or problems with the materials. Amperage too high for your wire feed speed is a classic cause, especially in MIG welding. That makes a violent, unstable arc that throws molten metal everywhere. Long arc length, holding the torch too far, will do the same. Contaminants on the base metal cause problems. Rust, oil, moisture. These can cause gas eruptions in the arc that lead to spatter. Using the wrong shielding gas can disrupt the arc. A poor gas flow rate can too. Now let's look at the opposite of undercut. Overlap. Overlap, or cold lap, is when weld metal flows over the base metal without fusing. Like pouring thick syrup on a cold plate, it just sits on top. This often happens at the toe of the weld, making a flap that's not connected underneath. That creates a mechanical notch, a perfect spot for a crack. It also adds no strength to the joint. It's a classic sign of moving too slowly or having heat settings that are too low. Preventing overlap is balancing travel speed and heat input. Moving too slowly makes the weld pool too large, and it droops or rolls over. Maintain a steady travel speed so the pool fuses at the edges without overflowing. A wrong torch angle can also cause overlap. If the arc isn't pointed into the joint, especially on fillet welds, metal piles up and overlaps. The fix: increase travel speed, or adjust torch angle to direct heat and fuse the edges properly. Welding isn't just about joining metal, it's about controlling it. When you introduce a massive amount of heat to a localized area, the metal expands. Then, as it cools, it contracts and shrinks. This uneven heating and cooling cycle creates powerful internal stresses that can pull and twist the metal out of shape. This is called distortion, or warping. It can turn a perfectly flat plate into a potato chip, or pull a carefully squared frame into a diamond shape. Fighting distortion is one of the biggest challenges in welding and fabrication, because you're fighting the laws of physics. The causes of distortion are rooted in how metal behaves when heated. The more heat you put in, and the slower you put it in, the more the metal will expand and then shrink. A long, continuous weld down one side of a plate is a guaranteed recipe for warping. The side you welded will shrink as it cools, pulling the entire plate into a curve. Similarly, making too many weld passes in one area keeps the heat concentrated, leading to more severe distortion. The type and thickness of the metal also matter. Thin sheets are much more prone to warping than thick plates, and some metals, like aluminum, expand and contract more than steel. So how do you keep things straight? The first line of defense is to minimize the total heat input. Use the lowest possible amperage that still gives good fusion and penetration. Use the smallest weld size that the job requires. A bigger weld isn't always stronger, but it's always hotter. Technique matters. Use intermittent or stitch welding instead of one long, continuous bead to help distribute stress. Plan your welding sequence. Alternate welds side to side to balance shrinking forces for large assemblies. Before you strike an arc, take prep steps to fight warping. Brace and clamp the workpiece firmly to a heavy, flat table while it cools. Pre-bend or preset parts opposite the expected distortion so the weld pulls the assembly back into alignment. This takes experience and a bit of guesswork, but it can be very effective. If distortion happens, you can sometimes fix it with carefully applied heat elsewhere, a process called flame straightening. But preventing distortion is far easier than fixing it. You can't fix what you can't find. That's where non-destructive testing, or NDT, comes in. These are the methods inspectors use to look for defects without having to cut the weld apart. The most common and powerful tool is your own eyes. A thorough visual test, VT, can spot many surface problems. Undercut, overlap, excessive spatter, large surface cracks. It's the first line of defense. For things you can't see, dye penetrant testing, PT, uses a colored dye that seeps into surface-breaking cracks or pores. It makes them visible. Simple, cheap, and effective for tiny surface flaws. When the problem might be lurking below the surface, you need to bring in the bigger guns. Magnetic particle testing, MT, is great for subsurface defects in ferrous metals like steel. The part becomes a temporary magnet. Flaws attract iron particles to reveal the location. For a true look inside the weld, you have two main options. Radiographic testing. RT, an X-ray for metal, shows slag inclusions, porosity, and internal cracks. Ultrasonic testing, UT, uses sound waves that bounce off flaws, creating a signal on a screen for a trained operator. The key takeaway isn't just knowing defect names. Almost every single one of them is preventable. Bad welds don't just happen, they are caused by moving too fast, not cleaning your material, wrong settings, poor technique. The foundation of a good weld is laid before you strike an arc. Start with a clean, properly prepared joint. Set your machine correctly, not too hot, not too cold. Use a steady hand. Maintain a consistent travel speed. Welding demands attention to detail. Take the time to get it done right. Learn the AWS limits for your work so you know what's acceptable. Inspect your own work as you go. Clean your slag between passes. Watch your puddle to make sure it's fusing properly. Listen to the sound of your arc. These small habits separate amateurs from professionals. Do the job right the first time, and you won't have to worry about a bad weld coming back to haunt you.